Of course, classification modeling is not restricted to decision trees. Many other classification methods are available, including naive-Bayes classification. Naive-Bayes classification methods are based on Bayes' theorem developed by Reverend Thomas Bayes. Bayes' theorem updates our knowledge about the data parameters by combining our previous knowledge with the information obtained from observed data, resulting in updated parameter knowledge, or what we call the posterior distribution. Consider a data set made up of two predictors x equals x sub 1, x sub 2, and a response variable y, where the response variable takes one of the three possible class values, y sub 1, y sub 2, and y sub 3. Our objective is to identify which of y sub 1, y sub 2, and y sub 3 is the most likely for a particular combination of predictor variable values. Let us call this most likely combination x asterisk equals x sub 1 equals x sub 1, x sub 2 equals x sub 2. We can use Bayes' theorem to identify which class is the most likely for a particular combination for predictor variable values by number 1, calculating the posterior possibility for each of y sub 1, y sub 2, and y sub 3 for the combination of predictors x sub 1 and x sub 2. Number 2, selecting the value for y with the highest posterior probability. Let y asterisk be one of the three potential values of y based on the given equation. Now, P, open and close parenthesis, y equals to y asterisk represents the knowledge we have about how likely the class value y asterisk is before we even begin. Since that information is known prior to our analysis, we call P, open and close parenthesis, capital Y equals small y asterisk, the prior probability. This prior information is combined with P capital X asterisk bar capital Y equals small y asterisk, which represents how the data behave when the response equals small y asterisk. The denominator P, open and close parenthesis, capital X asterisk is how the data behave without reference to the response class values, otherwise known as the marginal probability of the data. The result of the formula represents the information or idea we have about how likely our class value y asterisk is if we observe the particular predictor variable x or capital X asterisk. Since the information is updated from capital P open and close parenthesis, capital Y equals small I asterisk, after examining the data, we call P open and close parenthesis, capital Y, small y asterisk, bar, capital X asterisk, the posterior probability. What if we have no prior knowledge about the parameters? In this case, you can use a non-informative prior which says that every class value is equally likely. But using the non-informative prior, your posterior probabilities are based solely on the data. How can we use the Bayes theorem probability to classify a record? In our example, we have three different possible values of y asterisk. For a fixed value of x asterisk, we calculate a Bayes theorem probability for each of the three possible values of y based on the equation. The maximum a posteriori hypothesis tells us to classify the record x asterisk as the value of y which has the highest posterior probability. In other words, choose the class value of y that corresponds with the largest of the three posterior probabilities we calculated. If we have more than one predictor variable, then the class conditional independence assumption allows us to write P, open and close parenthesis, Capital X asterisk bar capital Y equals small y asterisk as the product of independent events. For example, say we have two predictor variables, we refer to this equation. To write, we will use this equation.